The same, but it's now recording my voice and when I click the slides. And this is just, it's kind of useful for you guys to know if you're rehearsing a talk, okay, or something that you might be doing. It's a good idea to do this, okay, so you can then play back the talk to yourself. And if you understand what you're saying, okay, that's like the first step of a good talk, okay? So kind of, there's a little top tip for you. Anyway. Right, so ICP techniques, we'll come on to what that actually is later, is a kind of a group of geochemical analytical tools that allow us to measure usually kind of bulk samples. So I think you guys have been down to the ion probe and the SEM, things like that. So those are the ones, techniques where you're wanting to measure spot analysis, so you want to measure the spatial variability in the chemistry or isotopes in the sample. But ICP techniques, you either want to take a whole rock, okay, and you have to kind of like powder that, dissolve it up in kind of like nasty acids to create basically a solution, or you might be able to kind of like separate out some crystals by like just picking them out, okay, or picking out some individual fossils from the sediment, and then doing a bulk dissolution of those. So this is the kind of things. So for ICP, you basically need to dissolve your sample. Okay, there are some exceptions to that. You don't have to dissolve the whole sample, so there are a bunch of kind of like scientific questions you might want to ask if you're just taking, so for instance, this is a series of soils and just leaching those with different reagents, okay? So you're not dissolving the whole thing, but you're dissolving some phase of it. So it's a technique for, you have to create a solution, okay? Okay, so there are laser ablation techniques where you don't have to create a solution, but for the most, the bulk of these things, you need to turn your sample from a solid geological thing into a liquid. Okay. Okay. So there are basically two kind of like schools of ICP. So when people say, "Oh, I'm going to measure it on the ICP," that's not a very useful piece of information. So there's basically two broad categories. There's optical emission or absorption, optical absorption machines. So that's OES or atomic absorption spectroscopy. And there's another class of ICPs that are mass spectrometers. And we'll see both of those today. We'll go down to the labs and see both of those. But they basically share kind of basically one component, which is this inductively coupled plasma. And then the rest of the machine is different in terms of how it kind of figures out what the chemistry is. Okay? So plasma ionization is the bit that they both share. So a plasma is kind of the fourth state of matter. So it's a mixture of, it's a kind of a gas. So it behaves a little bit like a gas, but the atoms in that gas are ionized, so you have a mixture of positive ions and electrons, okay, that are separated. Okay? So these occur, plasma is basically what you see in lightning, okay? And they are, because you have to separate the electrons from the positive ions, you have to have an extremely high temperature. Okay? And that's useful, so if you can create, so these are other examples of plasmas. If you can create a plasma, that means that you are creating a mixture of ions and electrons, and that's all we're doing, basically. We're using this inductively coupled plasma as an ion source. So we're using it to turn our sample in from kind of neutral atoms, molecules, into ions. Okay? And the way this kind of works is we have a idea of it here, but so this is the kind of the schematic of like your introduction of the sample. Okay, so you have to have something that your samples are in some like pots of solution, and usually those pots you basically suck up the sample, and it goes through a device like this, which is called a nebulizer, which is a bit like an aerosol spray, and that just turns your sample into a mist. Okay. So you have a mist of sample. Sometimes it goes through some glassware to remove the larger drops, or you might put it through another device that basically removes the larger drops. So you have when you actually introduce your sample aerosol into the plasma, it's not got lots of water in it. Okay? And the reason for that is that the plasma basically it has to be quite a pure gas to start off with. So this is the device which the plasma is contained within. So this is basically a series of glass tubes. Your sample is introduced up the middle tube, and then there's a tube around that, okay, which has got a flow of argon gas usually, and then what happens is that there's this coil that goes around the whole kind of fiasco, and through that coil you pass a very high frequency, so a radio frequency alternating current. Okay? And what that does is that creates this very strong kind of electromagnetic field, and it basically just excites the argon atoms. So it works in exactly the same way as a microwave. So a microwave has microwave radiation, and that basically vibrates water molecules, okay, and heats them up because that's all heat is, vibration. So all this is doing is basically shaking the argon atoms, so they get very, very hot and they ionize, and that's what's creating the heat that causes the plasma that allows us to ionize our samples. And then the last kind of tube on the outside is a tube which has just got a very, very high flow of inert gas. So that's usually, again, argon, because if you've got an argon bottle, you might as well just use that gas. And that basically keeps the plasma away from the edge of this glass tube. Because the plasma is at 6,000 Kelvin, okay, which is extremely hot. Okay? And if that touched this glass tube, it would vaporize the tube instantly, and bad times all around. So another issue, because this is so hot, okay, it's 6,000 Kelvin, that's the same temperature as the surface of the sun. Okay, so it's giving out intense ultraviolet radiation. Okay, so when we use these have to be in a box. Okay, because if they didn't, we'd all get cancer and a really good tan. Okay, so once we've ionized our sample, okay, you've probably done this kind of stuff already with the X-ray techniques. You've done X-ray techniques? Yeah, so this is the idea with the optical sample. Basically, your sample goes into this plasma, and then we basically just look at the light coming off that plasma. And what happens is that, say this is the nucleus of an atom. Okay, these are electron shells, and if you're electron, you're completely outside of this thing. You're ionized. Okay, but not all of the samples are completely ionized. Some of the electrons are only excited up to different shells. Okay, and when they drop back down into their kind of like the shell that they should be, they release a photon, and that photon is kind of like wavelength specific to the energy gap between the different shells. Okay, so that means that this at the top is an example for hydrogen. Okay, so these are the colour lines that hydrogen will give off as it's kind of progressively ionized and unionized and that kind of thing. Okay, so we can basically use the lines that we see to determine what chemical elements we have in our sample. Okay. And basically, the more intense the lines are, so the stronger the light coming off, the more of that element there is. That simple. So this is a schematic of that thing. So we have our plasma torch. Okay, so that's shining lots and lots of light, like a lot of light. So we don't want all of that light to go into our machine. So we basically bounce it off a bunch of mirrors. We have a collimator that makes sure that all the light is going in one direction. So when we basically put it through a prism, okay, like you probably did at school, it splits it into all of its different colours, and then we can basically just, all we do is, this is the same kind of camera chip that you have probably in your phone, okay, and that basically takes a picture of the spread out different lines, okay. And by the intensity of light arriving at each kind of like place on this camera chip, we can work out what elements are in our thing. Okay, so mass spectrometry has the same torch at the beginning that's producing these ions, okay, except we then have this section is different, okay. So I guess the ionization is the same, sample processing is the same. We still have to make it into a solution. Data processing is also kind of very similar, but we basically have to have something that discriminates a heavy ion from a light ion, okay? Because mass spectrometry won't tell you what chemical elements you have; it'll only tell you what different mass ions you have. Okay. Unfortunately, those two things are quite strongly related, but we can. Okay, so yeah, so this is the plasma source of that whole thing. It's really hot, and that's good because other types of mass spectrometer don't ionize all elements. So some elements are really, really hard to ionize. So for instance, thorium or thallium or tantalum, things like that, the T's mostly. They're really quite hard to knock an electron off. Okay, so if you wanted to look at kind of two different elements that one was hard to ionise, one was not hard to ionise, you try to measure them at the same time, it would be very difficult. Whereas the plasma is so hot, everything gets ionised. And it also is relatively matrix independent. So that means that you can put other things into, so your sample doesn't have to be very pure. So if you wanted to measure the amount of lithium in a rock for some reason, if you had a small amount of lithium in a lot of rock or a lot of lithium in a small rock, those extra elements wouldn't make so much of a difference. They do make a difference, we'll come on to that later. Okay. One of the disadvantages for mass spectrometry of this system is that this is very hot and is at atmospheric pressure. Okay, so it's because it has to be, because otherwise it wouldn't exist if it wasn't. If you put it in a vacuum, there would be no plasma there because the vacuum would suck the plasma away. And the mass spectrometer has to be an extremely high vacuum. Okay, so we have to have some really big pumps that basically we put a hole in the front of our mass spectrometer so the ions can get in. Okay, but that also means the atmosphere can get in. So we need to have a series of really strong vacuum pumps to pump that stuff away, which we don't have to worry about with the OES because that doesn't need to be at a high vacuum. Okay, so mass discrimination. So we create a beam of ions, and we'll go on to how that we do that. And we need to basically discriminate between the heavy ones and the light ones. So one way is to use a magnetic field. Okay, so you've probably done this at school. It's either the left hand or the right hand, it doesn't really matter. But a force that deflects an ion will be at right angles to the magnetic field and the electric current. So you can think of a beam of ions. Basically, you're just travelling a charged particle along a linear path. That's essentially the same as passing electrons along a wire. Okay, but obviously in the other direction because they're positive in this case. So a beam of ions will be deflected by a magnetic field. So this is a schematic diagram of, I think, one of the world's first mass spectrometers back in the early 20th century, and this doesn't have a plasma source. So this just had an electrode, a filament like an old-fashioned light bulb. Do you remember light bulbs that had filaments, right? So when those filaments get really, really hot, they start to give off ions from their surface, especially if you put a sample on them. And then all this system has has a really, really high voltage behind the filament, and that repels the ions away from it. Okay, so that those ions in this mass spectrometer, there's something clever to kind of focus them into a beam. So these ions are just kind of like sprayed down this way, and we basically just have a small hole here. So we create a beam of ions coming into this region of the mass spec here. And this kind of shaded region is a big magnet. So the magnetic field is going down into the page. Okay, so the energy which these guys are accelerated by, the basically accelerating energy is the charge on the ions times the voltage which they're being accelerated across. Okay, that's the amount of energy they have. Okay, and you can describe that in terms of kinetic energy. That's how fast those ions are going. Okay, so that's dependent on their mass, which will become important. Okay, so we could then come up with this equation here that shows that the mass of the ions and the voltage they're accelerated with, let's just add these two equations together. Pretty simple stuff. Okay, so this is the details of this are not really that relevant, but this is kind of, imagine this is the force that is accelerating our ions to bend, right? So this is basically the centripetal acceleration that's causing our ions to bend. If we had a magnetic field that was going down through here, our ions would go like that, but they get bent around by the magnetic field. Okay, and that can be kind of described thus. Okay, so the force. Okay, well, it's actually the acceleration up there. Acceleration is just the velocity squared divided by the radius which they're being turned through. Okay, so the so that the force of the force acting on each mass ion is kind of this equation. This is magnetic field, the velocity of the ion. So the faster it goes, the more it's bent. Okay? And the more charge it has, the more it's bent. Okay? And you can kind of then balance these two forces. So this is the to get this equation here. It doesn't. I mean, the details are I forget, but basically this is the outcome. Okay, so here's in this case this is actually a beam of electrons, but there's a magnetic field going through this kind of glass sphere, and you can see that they're being bent round in a circle. Okay. So you can basically combine those two sets of equations for this, which is the which is the one for the accelerating energy and the basically kinetic energy of the ions, and this one, which is basically how much the magnet bends stuff. Okay, and that's dependent on the charge, the strength of the magnet. Okay, determines basically the radius at which stuff is bent through. Okay, so what we can then, we've just rearranged those equations to basically show that the radius stuff is bent through is dependent on the mass, okay, and the accelerating voltage and the magnetic field. So the accelerating voltage usually doesn't change for any one sample. So if you put two different elements that had two different masses, okay, on this sample here, okay, they would have the same magnetic field, they would have the same accelerating voltage, but the bigger the mass of that atom is, the bigger that mass of that ion, the bigger the radius would be that they were bent through. Okay, so that means that we can then use, say, if we imagine we could have a bunch of different detectors at different kind of radius of things, and they would detect the different ions, or we could, I think the next slide, we could. So this is kind of a magnet. This is our kind of source. We could have a bunch of different detectors to detect the different ions. Okay, that would mean we have to have lots of detectors, which would be very expensive. Or we could detect one for a bit, and we could then change the magnetic field, and then detect another one for a bit. Okay, or we could change the accelerating voltage, and that would also change how fast it is bent. Okay. And also just to point out that we basically, in this case, if we're clever about the shape that we make our magnet, okay, if our ions are spreading out from our source, okay, we don't need to collimate them so much, because if we're clever with the way that our magnet is shaped, okay, they're in the magnet longer if they go up here than if they go along here, because our magnet is shorter at this end. So these guys get bent more than these guys. That refocuses our beam over here. So we can be clever with our mass spectrometry design to make it more efficient, to get more of our sample collected at the other end. Okay, so some of the advantages and disadvantages of this system is that if you change the magnetic field, if you wanted to look at one element and then another element by changing the magnetic field, every time you change a magnetic field and there are bits of metal near that magnet, that will induce a current in those bits of metal. Okay, that current in those bits of metal will create a magnetic field. Okay, which will oppose the change of magnetic field that you've just applied. So that means that when you change the magnet, it doesn't change to its new magnet power instantly. It takes a while to get there. Okay, so that means that if you wanted to change from measuring one element to another element, it's quite slow. Okay, so mass spectrometers that use magnets are quite slow in switching from one element to another element. And when I say quite slow, it might take maybe 0.2 of a second to measure all of the elements. Okay, that kind of slowness. So there are kind of ways around that problem, which we might go into when we go down to the lab later on. But the magnet's prone to drift over time. Okay, so it's a big piece of metal. You know, kind of, as it heats up and cools down, its efficiency changes, things like that. Yeah, so you can basically, if you want to measure multiple isotopes, you have to have multiple collectors, or you have to switch this magnet, and that takes a while. Okay, or you could switch the accelerating voltage. This is another thing you could do, which also has, which is faster, but is less reproducible. Okay, so this will come on to later. We might have a look downstairs. There's this issue with mass spectrometry, in that all it measures is basically the mass to charge ratio. And usually you can pretty much say that almost everything will have a mass of a charge of 1 or 2, so that's pretty fine. But it doesn't tell you what element you're looking at, or what molecule, for instance. And this is more of a problem if you're looking at molecular mass spectrometry, where you're actually measuring ions of molecules, but it's also a problem when you're trying to measure elemental stuff, is that some elements have masses that are the same as other elements, so it's very hard to distinguish them apart. Okay? And also some molecules have the same mass as other elements. So for example, I've been doing some work with someone in chemistry. We've been measuring phosphorus by mass spectrometry. Phosphorus has got a mass 31, okay? But we measure that in a solution of nitric acid, and nitrous oxide, which gets basically broken apart from the nitric acid in the plasma, has got, made up of nitrogen, which has got isotopes 14 and 15, and oxygen, which has got isotopes 16, 17, and 18. So there is a combination of those isotopes that gives mass 31. Okay, so if we want to measure mass 31, we can't tell if it's phosphorus or this molecular nitrous oxide. Okay, there's a solution to this in that I just said that they were the same mass. They're not exactly the same mass. So if we have a very, very precise mass spectrometer that can tell the difference between very, very small, so 133.046, and in this case 133.096, so very small differences in mass, we can actually resolve. So it turns out that the phosphorus and the nitrous oxide actually do have slightly different masses. One is kind of 31.01 something, the other one is 30.99 something. Okay, and if we have a mass spectrometer that can separate out those masses enough, okay, then we can basically resolve those differences. I'll ignore that. So there's this other kind of way of separating out your masses, and that's using this device. Okay, so this is a quadrupole. Okay, so this is probably one of the most common kinds of mass discriminator for almost all mass spectrometers. It's certainly the most common for ICP, or in plasma mass spectrometers. This was the kind of discriminator they put on mass spectrometers that they send to like Mars and stuff, because it's really super stable. So instead of using a magnet to bend the ions, we use electric fields. Okay? And actually the slide before, which I skipped over, basically shows that the electric field doesn't actually discriminate mass at all. Okay, so mass cancels when you work through all the equations. But it turns out that if you have a magnetic field, an electric field that's alternating, okay, then it will discriminate in terms of mass, because the so I'll just go through and explain. So this so the way this works is basically you have a series of poles. So these are basically just metal rods. Okay, they're not actually circular in cross section. They're more kind of like hyperbolic, but you know that doesn't really matter. And two of the rods that are opposite each other have a negative kind of charge on them, and two of them have a positive charge on them. Okay, so that's this U term here. Okay, and then they, in addition to those kind of DC charges, they also have an alternating kind of charge. So superimposed on these kind of like static charges, they also have this high frequency alternating current field. So what happens if we just think about the static charges? If you have these positive guys here, we have a beam of positive ions going through those there. Okay, so those are going to repel the ions, right? Because the ions are positive. So that basically pushes the ions in towards the middle. Okay. So that kind of focuses down this beam. Whereas this guy up here, okay, this will spread them out because it's negatively charged and it's basically pulling the ions away from the centre of the current. Okay. But then if we think about the alternating currents, or the alternating charges, with this pole here, okay, we're pushing stuff towards the middle, but if we're alternating current as well, if that's big enough, that's going to start superimposing on this positive charge occasionally kind of negative charges. Okay? So it's going to start to accelerate ions away from the middle. Okay? And it will do that faster for the lighter ions because they've got less momentum, so they get more easily dragged out to the sides. Okay? So if you just look at these guys, okay, this will only allow the heavier ions through because the lighter ions will get kind of wiggled out towards the sides. Okay? Whereas with these guys, it's the opposite case. So in this case, we've got our ions are being pulled apart. The ion beam is being pulled apart. Okay? But the heavier ions, so the lighter ions, will be more determined by this alternating current. So as they get close to this thing, they'll be repelled away from it. Okay, and they'll be repelled away from it fast enough to overcome the kind of the static charge. So these allow the lighter ions to go through, and these allow the heavier ions to go through. Okay, so that means we have basically a high pass filter and a low pass filter. So we can play around with either the static voltages, or the alternating current voltages, or the frequency of the alternating currents to choose basically what mass is allowed to get through. Okay, so just think of it, it's basically a high pass filter and a low pass filter. I mean, it's got lots of dials on it. Okay, so you don't need to worry about that because when you go and use a mass spectrometer, you basically, all of these parameters have been calibrated and you just say what mass do you want to let through. Okay, so because this doesn't have any magnets in it, okay, it can switch between measuring different masses very, very quickly. Okay, so it can measure stuff very, very quickly, which is great, but it doesn't have a very good mass resolution. Okay, so it can only really measure the difference between whole masses. Okay, so and there's lots of text, which is texty, and that's what they look like. So that's quite a big one. So they're just 4 metal poles, and the ions make it down in the center. So just a little bit on ion detection. There are a number of different ways that you can detect whether an ion arrives. Your ion beam. These are ion counter devices. So all these do is they basically try and register the arrival of each individual ion. So every charged atom that comes in, it just tries to count it. So this is an old-fashioned kind of type. It's called a daily detector after, I guess, somebody called Daly, where an ion beam comes in, and this is basically set to a ridiculously high negative voltage. Okay, so like minus 10,000 volts. So as soon as your ion beam enters this chamber, it's basically attracted to this metal thing, okay, and that's coated with something that when an ion hits it, it basically gives off an electron, and then that electron is basically detected by it hits a phosphor screen, and that goes flash, and then you have a photo multiplier that goes, there was a flash, okay, and then it waits for the next one to go, another flash, and you just count them, okay. And this is a similar device where an electron comes in and heats one of these. Basically, this is a metal plate coated with kind of magic paint, which no one knows what it is, but it's basically magic paint. And every time an ion hits it, it gives off a shower of electrons. It goes, oh, get off! And that basically hits some of those electrons hit another plate, which goes, more electrons, and gives off even more electrons. Okay, so it basically creates this cascade of electrons to create something that's big enough that we can measure as a pulse of current coming at the end. Okay. So the advantage of these is that they're really, these kind of detectors are really good because they can detect the arrival of an individual ion, so they can measure really, really low levels, really small ion currents. But they do have a bunch of problems with them. In fact, so when, for instance, this cascade is going on, if another ion arrived, it wouldn't notice. Okay, so at very high, when you have lots of ions arriving, okay, their efficiency goes down. Okay, so you need to calibrate for that when you're making your measurements. So the simplest type of detector, and this is kind of this was in the earliest mass spectrometers and is in kind of is in the mass spectrometers we have downstairs. as well as the other ones, is it's this thing called a Faraday cup. And it's going to be that old, it's named after Michael Faraday, right? So it's just a bucket coated in carbon, and when ions come in, okay, they basically hit the carbon surface, and basically electrons have to come from somewhere to neutralize those ions, okay? So basically that creates a current from Earth, and you measure that current across a resistor with a voltmeter. They're really, really simple. They're very, very stable. They can work up to very, very high beam currents. You can measure really big intensities of them. If you have, so with the other ones, if you had one ion counter and another ion counter, their efficiency might not be the same, so you have to calibrate for them. These are always identical because they're so simple. So you're just measuring the actual current of the ion beam. Right, so, I mean, why do we do this kind of thing? So, mass spectrometry can tell us about elemental abundance or isotope ratios. The optical emission spectrometer can only really tell us about elemental abundance, okay? We'll talk a little bit about detection limits. So this is basically the smallest sample that you can measure. Okay, and this is important for some, if you're looking at particularly environmental samples that might have very low concentrations of stuff, okay, you might have to use mass spectrometry rather than the optical method because it's a little bit more sensitive. And you know about all of the uses for chemistry. Okay, so I've kind of explained how these kind of machines work, but there's this kind of like problem in that the thing that they produce is either maybe the intensity of light for the optical emissions, okay, or it might give you how many ions per second or voltage is produced by the ion beam, okay, and that is totally meaningless. That means nothing. Okay, what you want to know is how many micrograms per litre is in your sample, or parts per million. Okay, you familiar with the term parts per million? Do you know what it means? What is it parts per million of? Is it how many atoms you have per million atoms? Yeah. Usually, it's how many grams of the thing that you want to know is in how many grams of your sample. Okay, so for instance, kind of 1 part per million uranium. There's actually a lot less uranium than if it was 1 part per million lithium, because there'd be more atoms of lithium because it's less mass. Okay, so it's mass per mass. And another thing that you might want to think about in terms of that it's kind of a little bit tedious and important is that in mass spectrometry, when you're doing things by dilution and running in solutions, you measure things in micrograms per litre. So that's the same. That's almost like ppm, right? There are almost 1 million grams in a litre of water. But what if your solution isn't water? What if it's seawater that's a different density? Okay, so converting between kind of units that are mass per volume and mass per mass, or moles per mole, or moles per litre, or moles per gram is a nightmare. Okay, so this is one of the places where you're reading a paper and you're thinking, well, this person's measured it in these units, one person's measured it in another units. They say they get the same number, but they shouldn't be the same number because there's a conversion factor that they've not thought about. Okay, so this is where geochemistry goes bad. Okay, so this is the kind of question. We might over time measure a bunch of different samples, and we might get like signal intensities as we put our samples in the mass spec or the OES, and we want to turn that into basically the concentration for each sample. Okay. So what we have to do is we have to standardize our techniques. Okay, so we have to do some kind of calibration where we have a bunch of standards that we know the concentration of, okay, and see what intensity we get out of the machine. Okay, that gives us a calibration curve. Okay, and then we can measure something that we don't know the concentration of and read off the graph. We don't read off the graph, we work out an equation and do some maths, right? But you could do it by reading off the graph. So some things to point out on this graph is that this, at the moment, we've got a linear response here. So for like doubling the concentration, we double the intensity. Okay, but sometimes this response starts to not be linear, and that might be because we're putting maybe so much sample into our machine that maybe it's inhibiting 100% ionization, or we're starting to block, like clog up the cones of the machine, stopping stuff getting through. So we have this thing called limit of linearity. Okay, so that essentially means that you can't really, if you've measured a whole bunch of standards, okay, you need to be sure that if you can't measure samples that will be up here. Okay, so you can't measure samples that are outside your range of calibration. We've got this concept of limit of detection and limit of quantification. So this is the smallest sample that you can tell is there. You can distinguish from just the noise of the machine. Okay, and the limit of quantification is basically the smallest sample that you can not only tell it's there, but you can say what the concentration is. Okay, and we'll just I think the next slide is more descriptive of this. So imagine we measured we wanted to know the concentration of cadmium in river water or something. Okay, so we would also want to measure what the lowest concentration possible we can measure it. So we put into the mass spectrometer just pure water that we sure had no cadmium in it. Okay, it's the cleanest water we could get. So we'd measure that a bunch of times. Okay, and that would give us basically our blank measurement. Okay, so this would be our average blank, and this measurements might vary by some amount. Okay, so if we then put a sample in, okay, then if we got a measurement here, okay, we are kind of 99% sure, okay, like 3 standard deviations, that sample is bigger than the blank distribution. Okay, but if we had a sample that was that concentration, there is quite a high chance that it's actually just blank. Okay, when we measured it, we might not see that it's there. Okay, so that means that at 3 standard deviations, we can kind of tell that something is a bit higher than the blank, but we can't be absolutely sure that it isn't just a flyer. Or if we did have a sample that was that concentration, it might come out to be lower than the blank. So really, we need to move out to much further, and there's this kind of thing, like a rule of thumb. A convention that you basically look at 10 standard deviations away from your blank, 10 standard deviations of the blank away. If you get something that's here, you can not only say that it's definitely bigger than blank, but you can quantify that difference. Okay, so that's the reason why we have these limits, and that defines what the dynamic range is. So the lowest concentration sample you can measure, and the highest is the limit of linearity. Okay, so we could do that, but there's this problem that if we put, say, a series of standards in that are, say, pure cadmium in dissolved in nitric acid, so almost nothing else in the solution, and that might give us a calibration line like this. But then if we put a bunch of samples in that have got loads of other stuff in there, so say for instance seawater, which has got loads of salt, okay, all of those other elements, they'll start ionizing, take some energy out of the plasma, they might change the temperature of the plasma, they might have all kinds of crazy effects that might inhibit kind of the intensity of measurement of any element in that sample. So basically, if your sample's got lots of stuff in it, total dissolved solids, it tends to suppress the signal. Okay, so that means that if we tried to measure something, okay, and we got an intensity like that, its concentration would appear to be much lower. Okay, so this is a problem. Okay, so I drew some lines on there. Look at that crazy animation. So we have this technique called internal standardization. So what we do is we add an element to our sample that isn't really in our sample already, and we're not interested in measuring. Okay, and quite often we use indium because nobody is interested in the geochemistry of indium. It's a very boring element. And it doesn't have many interfering masses or anything like that. Okay? So if we add enough of that element to our sample that it massively swamps any natural indium that was already there, okay? And we add exactly the same amount to all of our samples, okay? So it doesn't matter how much we add, as long as we add exactly the same amount to each of our samples. Instead of measuring signal, if we measure the ratio of signal of the element that we're interested in, cadmium, to the ratio to the signal of indium, okay? That means that for these samples that have had their signal suppressed, okay, the signal will be suppressed for the element you're interested in and the indium, okay, and hopefully by the same amount. That's not always true, but which is why you might want to choose a different internal standard that behaves chemically more similar to your element of interest. But kind of just as an example, if these are both all suppressed by the same amount for indium and say cadmium or the element you're interested in, if you measure the ratio, everything plots back up on a calibration line. But this time our calibration line is against the ratio of two intensities or counts per seconds rather than just the intensity. Okay? So this is a really common approach, okay, and is actually a very simple and easy thing to do. Okay? You just have to know you're adding the same amount to every sample. Okay, so moving on to some more problems. So I mentioned this problem of transmission efficiency in terms of some elements are suppressed. Okay? Turns out that it's not just an elemental problem. So this is a schematic of one of the mass spectrometers we have downstairs. Our sample goes in here, okay, and it gets sucked in through a high vacuum and accelerated across a really high voltage, an ion beam, and it gets bent once by an electrostatic field, magnet, and then some detectors down at the bottom. Okay? So as it does all of this, okay, if you've got 100% of your sample, maybe 90% of it makes it to here. But getting through this tiny hole is really inefficient. Okay, so maybe 2% of your sample gets to this part of the mass spectrometer, 1% to this part, and actually this part's quite efficient, okay, because this is a super high vacuum. So only 1% of our sample actually makes it to the detector. Okay, that's okay if it's 1% for everything, okay, but it's not. Okay, so it's slightly different for different elements, but also it's different for different isotopes of the same element. Okay, because the heavier isotopes will have more momentum as they go through here. Okay, so it's easier for the heavier isotopes to get through. And this is a problem. For instance, if we were measuring lithium isotopes, which are, good thing to measure if you're interested in weathering. The natural abundance of lithium isotopes, the lithium-7 divided by lithium-6, is about 12. Okay? When you measure them on a mass spectrometer, you might actually just measure a ratio of about 15. Okay? So you get the wrong answer, right? Which kind of is dumb. Okay, so what we have to do is we have to correct for this isotopic fractionation. We have to correct for this preferential treatment of the heavier isotopes. So these are, okay, so we can do that through internal or external standards, and we'll go through those. So I think first, so this we'll do through external standards. So imagine this is time. It says time in seconds, but imagine that's hours. Because when I was making this plot, I was an idiot. So we might measure a whole bunch of different samples through time, okay, and get some kind of like ratio about 15, okay, and we know that all of those numbers are wrong and meaningless. Okay, so what we do is we measure a standard that is the same. Okay, so this is basically every red dot here is the measurement of the same solution. Okay, and we're just measuring it before and after every sample. Okay, and we can see over time we get, so this red symbol, it should only have one value because it's one pot of solution when we're putting it in mass spec. But you can see it's varying over time as the mass spectrometer is kind of maybe heating up a little bit, cooling down, changing shape slightly. Conditions in the plasma might be changing. So that kind of doubly means that these numbers are meaningless because not only are they not staying the same, but they're giving the wrong value entirely. So what we do is we use this equation down here, which is kind of you should be really familiar with now in terms of the delta notation. We're basically looking at the difference in the isotope ratio between a sample and a standard. Okay, so that means that our standards now come out at 0. Okay, So they're not exactly 0 because these are standardized to the average of each standard measured either side of them. And we now have all of our samples are now giving the isotope ratio, not the one we measure, but the ratio that we measure relative to the standard. Okay, so relative to our standard. Okay. So this is quite useful because if everyone uses the same standard, we can all agree on isotope ratio. Which is another important thing to think about, is everybody using the same standard? But it also allows us to get an idea of how accurate we are at measuring stuff. Okay, so if you measure the same sample over and over again, that gives us a good estimate of our reproducibility of that measurement. Okay, so it's a good way of measuring the precision of your measurement. If you measure the same thing over and over again, how much does it vary? Okay, and you can do that for samples, or you can do it for the standards. Okay, standards is usually you get smaller error. Okay, so we'll go through some more problems with mass spectrometry now, and just go through the example of strontium isotopes. So you've probably done strontium isotopes to death, right, in other courses. They're really useful for all kinds of geological and environmental problems. So different parts of the Earth have got different strontium isotope ratios. You should know why. And you can either maybe look at them through time, so measure fossils from the ocean. That might tell you something about the balance of weathering versus volcanism. So this is an example looking at a tooth from some fossil dude, or dudette, not entirely sure, from France. So this is a map, in this case, of the strontium isotope composition of that tooth. And they tried to figure out where that person lived based on the different strontium isotope composition of different parts of Europe. And this particular study showed that it doesn't work because you basically you change the strontium in the tooth after the person dies. So you basically take that strontium into your tooth after they die. But anyway, so there are a whole bunch of reasons why you might want to measure strontium isotopes. Okay, so one of the problems we've covered is this mass bias. Okay, so we're preferentially measuring more of the heavier isotope than we would normally. Okay. So we could standardize our measurements with an external standard. Okay, so we could measure a strontium isotope composition that we know either side of our samples. Or it turns out that what we can do is in this case we're actually only interested in the ratio of 86 to 87 strontium, right? Because that's the one that varies a lot in nature because of the radioactive decay. Whereas the 88 to 86 ratio does not change. Okay, because they're not radioactive. So we could use, because we know what this ratio is, we could use that to correct this ratio. Okay, because the mass bias or the preferential treatment of the heavier ions should be predictable for different differences in mass. Okay, so we could do that. That would get rid of that problem. Okay, and there are equations for doing that if you really care about equations. But then there's these problems of interference, as I mentioned earlier. So these are the isotopes of strontium, 84, 86, 87, 88. Okay, so that's great if we could measure those, but unfortunately our sample is likely to contain rubidium as well. Okay, and that has an 85 and an 87. So that, if we measured that, that would kind of give us the wrong ratio by a lot. Okay, and then because we're using a plasma to measure our samples, okay, the gas will contain krypton. Krypton has mass 87, 85, 83. Okay, so if we now measure the 86, 87 ratio, we definitely will get the wrong answer. Okay, which will be done. It's worse because there's also, if you have double charged ytterbium, that will also have the same mass to charge ratio. So that ruins us there. It's worse as well because you could also get other elements that form molecular compounds in the mass spectrometer. So if there's any germanium, and there'll be oxygen in the plasma because it's not water, it's got oxygen in it. Okay, so that means that we've got all these other things that are really not making our life any easier. Okay, so how do we fix this problem? Okay, so we could do something to our sample to remove all of the other elements. Okay, and that's one thing that people do. Okay, and this is how we do it. So we get our sample, we dissolve it, we put it on top of a column of basically sand, okay, but it's plastic sand with special organic goo on it. And these work just like kind of chromatography when you were 7. Okay, You put the sample on the top, you pour acid on, that washes the sample through, but different elements come out at different times. Okay? So you then just collect the bit that has the strontium in it and doesn't have the rubidium and the germanium and all that other stuff. So that allows you to isolate the element you want. This is tedious and takes a long time. So you can't take out the krypton that way because that's a gas, and you introduce that when you do the mass spectrometry. So what you do in this case is that you find some isotopes of krypton that do not have anything else on them, any other masses here, and you measure those, which allows you to work out how big this bar is here. Okay, and then you just mathematically remove that from your measurement later on. Okay, so that's pretty good. So that's how we get rid of the interferences. We also, particularly one of the problems with introducing samples by solution is that your sample goes up a tube, okay? And then when you put the next sample up to that tube, there will be bits of your old sample in that tube, okay? And this is basically this concept of memory. So this is, over time, we start sucking up a sample, it comes into a mass spectrometer, we get some signal, then we stop sucking it up, okay? And we just suck clean acid, okay? And it takes a while for our sample to wash out. Okay, so that's a problem. There's some things. So if you measure another sample straight away afterwards, it would be, we get too much signal because we'd have the signal from our new sample and our old sample at the same time. So we need to make sure that when we make our measurements, okay, we just allow it to wash out, okay, until it goes back to the background level, okay. And this is important because this is one of the things that determines how long it takes to measure stuff, okay. Okay, so another good thing to do is to make a measurement of the memory before you measure your sample. So rather than measuring that to the baseline, you measure that to that. Okay, that allows you to so you basically have to measure the memory as well. Yeah. Okay, so kind of to summarise all these things, basically, if we have interferences, that gives us more signal. Okay, that ruins our calibration curve. If we have matrix effects, that suppresses our signal and ruins our calibration curve. Okay, but we have ways around these problems. Okay, and it's those ways around these problems which kind of maketh the geochemist. Okay, anyone can buy a mass spectrometer, right? But making this line a straight line is difficult. Okay, so this last series of ways around this is this concept of standard addition. So this is a way of making sure that, and I said this problem of when we added the internal standard to kind of correct for that suppression of signal, okay, that only works if the standard element and the element you're interested in are suppressed by the same amount. Okay, so there's a way around this, okay, called standard addition. Okay. And standard addition is basically you take your sample and you use your sample to do the calibration as well as the sample measurement. So the way this works is you get your sample and you divide your sample up into at least 4, hopefully 5 different aliquots. Just divide it into, yeah, that you know. And then you add a known amount of the standard of the element that you want to measure to each of your aliquots of the sample, okay? Then you make them all up to the same volume and stuff. Okay, and then what you do is then you just measure the intensity of all of these different different aliquots. Okay, so this is the one that you added no extra standard to, so no extra of the element you want to measure. This one you added a bit to, you added a bit more to this one, lots to this one, lots to that one. Okay. Now, because these all have the same matrix, okay, they all have the same total dissolved solids, the same bulk elemental composition, the same viscosity, because they're all made up of the same sample. All they have is different amounts of this standard element in them. Okay, so that means that none of these measurements is going to give us the concentration of our sample. But what we can do is you can basically work with the mass. It actually turns out that if you've got on the x-axis here the concentration of the stuff that you added, okay, the intercept here is your sample concentration. Okay, so this is great because this measurement will be very, very accurate because it gets rid of all of that matrix-dependent bias on the samples. So this is really good for measuring samples which are very, very different to standard solutions. So for measuring things like seawater, for measuring kind of like organic goo that chemists produce out of their experiments and that kind of stuff. The problem is that it takes 5 times as long than it does to measure a single sample. So it's 5 times as expensive. Okay, different concentration sample, stuff. Right, so there are a whole bunch of other problems we need to worry about. So the detector background noise, not really that important for most applications. It's basically, if you don't put any sample into your mass spectrometer, for some of these really, really sensitive detectors, they'll still detect something. Okay, so you need to worry about that. Tailing of big peaks on small peaks. So this is basically if you've got a really, really big ion beam next to a small ion beam. So if you had maybe uranium-238, very, very big beam, and you're trying to measure uranium-235, very small beam. Okay, that really big intensity beam, it won't just be at mass 238. It'll spread out over a wide range of masses because some of the ions, as they go through the mass spectrometer, get slowed down by interacting with other atoms in the mass spec, and that means they're slowed down, they get bent more, so they don't appear at the right mass. It's not that important. But one of the really important things is this thing called blanks. So if you're measuring, say, the amount of stuff in a rock, okay, when you make that measurement, you also add in all the, so in this case we're measuring lead in the rock, there's going to be lead in some of the acid, there's lead in lab dust. Everything you do to the sample will contaminate it with the element you're trying to measure. So this is a really important question when you're kind of designing an experiment. If you want to go out and kind of like collect a sample, okay, you want to make sure that there's enough of the stuff in the sample that you collect to be bigger than the amount of stuff that you add to it when you process the sample. So what we have to do is basically, we want to know what's in the sample. This is what we measure. We measure what's in the sample plus all this stuff we've added. Okay. So all we have to do is basically make a measurement of. We basically get a clean pot and pretend it's a sample and do everything to that pot that we would do to a sample. We add acid to dissolve the stuff that's imaginary in our pot. We do all this filtering that we might do. We do if we do exactly the same to this, which we do to this, all we need to do is minus this measurement from our sample measurement, and that'll give us the amount in our actual sample. And just briefly, I'm sure you've been through this kind of thing in other courses as well. This is kind of what we kind of want to know. We want to be precise and accurate. So we want to get the right number. We want to have a small error bar on it. Okay? So if we measure the same sample over and over and over and over again, okay, that tells us about our precision. Okay? How reproducible is that one measurement? Okay? Okay, what it doesn't tell us is, are we getting the right number? Just getting the same number and over again doesn't mean you're necessarily getting it right. Okay? And obviously you don't want to be any of these things. Okay? And the way we go about that is we have reference materials. And you've probably done this with the other measurement techniques as well, so I hope you would, is that we have standards which are, say we go to the chemistry shop and we say, can I have a solution of cadmium that is 1 ppm? And they'll go, there you go. And it basically, some poor bastard has got some cadmium and weighed it out on a balance and then weighed out some acid to dissolve it. And that has and you get a certificate with it and says this solution is this concentration. Okay? And we would use that to convert our counts per second or whatever it is into concentration. Okay? So that's what a standard is. The standard converts our machine output into a concentration. Okay? So we also have these, as a huge variety of these other things, which are reference materials. So reference materials are also things you go to the reference material shop for and you go, can I have some of the reference material? And it's like, could be a basalt, it could be some coal, you can get reference materials for water, you can get reference materials for almost, I think you can get like reference materials for things like bananas and stuff like that. You can get the standard reference banana. And you get those things and you measure those with your samples, okay? And although you already know the concentration of them, so you're not using these to correct your sample measurements for, you're using these to see if you get the right answer. Okay? So a really important thing when you're looking through geochemical papers, okay, and someone's come out with a new method for measuring, unobtainium in bananas, for instance, you say, right, well, have you measured the reference banana? Do you get the right answer? Okay, so so what you should almost never do is measure your samples with your standards, and then measure some geological materials or reference materials and get the wrong answer. Go, I'm going to correct. You could just do like, if every time you make a measurement you get a value that's like 50% too high, yeah, you could make a nice linear correction for that. You should never do that. Okay, although people do. So yeah, so that's where today's kind of like lecture ends.